14.4 is on the chain rule. So first we will look at the chain rule with single variable. So recall, if you have f of g of x like that, then we look at the derivative d dx of f of g of x. So you have a composite function, one inside of the other. Then you have to do the derivative of the entire thing. So we say that is f prime of g of x times the derivative of what's inside times g prime of x. So for example, if we have d dx of sine squared x, then that's really, right, sine quantity squared. So that's really 2 sine x, and then it's a 2 up there, so you do 2 minus 1, times the derivative of the inside, which is just cosine x. So it's just 2 sine x cosine x. Okay, so now we'll look at basically two different cases. One, when there's a single variable like embedded all the way inside the function. There's both the same function, and then we have the partials, which are different functions. So two slightly different cases. So the theorem says something like this. So let w equal f of xy, where f is differentiable for xy. If x equals g of t and y equals h of t, in other words, x and y are both functions of t. So just the variable t is embedded in both of those. Okay, and those are differentiable too. So where g and h are differentiable functions of t, we consider that one independent variable case. One independent variable. Then you get this chain, basically. We say dw, and then it's just dt. Now I'm using d because it's just one variable. So dw dt is equal to the partial of w with respect to x, and then we say dx dt plus partial of w with respect to y times dy dt. So that's the chain rule, how you expand it out with one independent variable and two dependent functions. So let's look at an example. Let's let w equal the natural log of u plus v. And then we're going to say u and v are functions of just one variable. Where u, let's see, what did it say? So where u is equal to e to the negative 2t, and v is completely different, t cubed minus t squared. And then we have just one variable, or one independent variable, embedded all the way inside. Well, there's just two things inside, but still. So what I want you to do is first write out the expansion with the correct variables. So you say the directions here would be to find, and it's a dw dt. because it's just one independent variable. So then expand out dw dt. Say dw dt, and then you got to hit each partial once. So you do partial w with respect to u, then you got to say du dt plus partial w with respect to v times dv dt. So that's what it looks like. So dw dt is partial w with respect to u du dt plus partial w with respect to v dv dt. And then now you use the actual functions, and you can do them separately and then plug them in, substitute in, either way, really. I'll expand it. It's not that bad. I'll just expand it out. So we'll just say that's equal. Let me erase that. So let's just say that's equal to, down here, and then we'll do the expansion. So derivative of natural log will be 1 over the u plus v times the derivative of u with respect to t. Well, no, it's only t, so it's just dw dt, right? dw dt. And so that is negative 2 e to the negative 2t plus 1 over u plus v. And then now we're doing this derivative. I hit the wrong button. There we go. Now this derivative. So that's just 3t squared minus 2t. Better put parentheses to be clear. All right, so then we can add that together and then substitute for u and v. So this is equal to this whole numerator. So that's what? 3t squared minus 2t minus 2e to the negative 2t all over u plus v. And then we can simplify that. Just take out that division bar. So that's equal to all that numerator, 3t squared minus 2t minus 2e to the negative 2t all over u plus v. So u is e to the negative 2t, and v is t cubed minus t squared. So e to the negative 2t plus t cubed minus t squared. Okay, next is two independent variables, and then you basically from there extend it to the same principle, same concept, any order after that is the idea. Okay, so next theorem, it's really just a formula, but this is two independent variables. And then it would be the same principle, same concept if you extended it to 3. So let w equal f of xy. F is differentiable. And then we'll say x is a function of two variables, s and t. And we'll say y is a function of two variables, s and t. Same two variables. Then you have to do partials. So you can't do just a derivative. You can't say dw of anything, because when you drill down all the way, you have still two independent variables. So we say partial of w, and you have to pick now one or the other. Is it going to be s or is it going to be t? So partial w with respect to s is equal to, and then the same principle here. We're going to say the whole thing first, so that's partial w with respect to the one of those variables, so x. And then now that's got to be a partial x with respect to s plus partial w with respect to the next variable, y, and then partial y with respect to s. One thing to look for is these should be the same, like that. Okay, and then now try what would partial w with respect to t be. Okay, so try that one. So you get partial w with respect to x, partial x with respect to t now, plus partial w with respect to y, partial y with respect to t. So you gotta hit each one as you go, but when you drill down all the way, you gotta pick one. Is it going to be s or is it going to be t? And then of course these need to be the same. Okay, so we gotta look for that. Then now you could expand that to, I mean, you don't have to have w, or you could have different variables. And we want to expand this to kind of any case or situation. So now let's look at a number of examples. So let's let w equal r cubed plus s cubed. And we're going to have r be pq squared, and s will be p squared sine q. Okay, so find partial w with respect to p and partial w with respect to q. Okay, so this is where I want you to try it. Shouldn't take more than that. So write out the expansion first. Okay, so we get partial w with respect to p. So this is still the same case as above, because r and s are just functions of two variables. They're not adding like another one, which the next case I'll show you, we add like another variable. So write out your partials. So this is partial the whole thing, which is w, with respect to, now pick one. Well, we're going to p, so now you got to hit each one of these with respect to p. With respect to p, and then partial. Oops, I messed it up. Not p. r, and then partial r with respect to p, plus partial the whole thing w with respect to the next one. Got to hit each one. With respect to s, and then partial s with respect to p. So now let's calculate those. Excuse me. So partial w with respect to r is just 3r squared. So it's 3r squared. And then partial rp, that'll just be q squared. Plus, and then 3, partial ws is just 3s squared. And then sine p is just 2p, and you just write in sine q. That's just a constant. And then you can substitute for your variables. 3r squared. Well, wait, I didn't do that. Oh, I just simplified that. That's all I did. Okay. Right, so all I did here is just said 3r squared q squared plus 6s squared sine q. So what you could do here, and this is pretty obvious, you could go through and substitute for your r is all of this, and for s is all of this. Okay, and it doesn't really matter. I mean, you can substitute in there. It's not necessarily better. Okay, try the next one. I'll leave it up to you. Partial w with respect to q. So write that all out. I don't actually have it in my notes at all, so you're on your own for that one. Well, I mean, I could obviously do it, but let's try another one because they kind of get more complicated. Let's take a look at those. All right. Next example. Okay, so I'll just say etc. Continue, try that one. Next one is multiple variables here. So find, we're just going to do one. Find partial w with respect to z if w is equal to r squared plus sv plus t cubed. And now I got to give you r, s, v, and t. So this is basically, this is w is a function of r, s, v, and t, each one of those. So when I simplify that, I got to give you each one of those. So you say r, I'm going to say r is x squared plus y squared plus z squared. S is xyz. V is x e to the y. And t is y z squared. So we recognize here that r is a function of x, y. They're all a function of x, y, z. S is a function of x, y, z. Even if it's missing a term, it's still x, y, z. V is a function of x, y, z. And t is a function of x, y, z, like that. So that's what you are saying or assuming, even though the variable is missing. So, but when you do the partial, you just end up doing that partial. So now, let's expand that out. All right, so this is where I'd want you to try it again. Okay, so try it. And expand it. All right, so we're going to write partial w with respect to z and expand that out. So you got to do, here's your parent function, the big one, and you got to hit each one of these as partial r, partial s, partial v, partial t, and then you got to drill down to your x, y, z. Now we're drilling down to z. So all we're going to be looking at is all the way down to z. Where's our z function? Right here. And take the sine 2. Here's z. No z here, and then here's z. So when you get to the v, that's going to be 0. All right, let's take a look. So it's partial w with respect to r, partial rz, plus partial w with respect to s, partial s, partial z. So it's always going to be z in the end, plus partial w with respect to v, partial v z, plus partial w with respect to t, partial t z. So I'm going through and I'm making sure I'm hitting each one. So here's R, here's R, here's S, here's V, and here's T. And then it's a partial because, right, each one of those is just a multiple variable. So now you go through and take each partial. Okay, so this is equal to partial W R will just be 2R times partial, it looks that's an R, not a V. Partial R Z is just 2Z plus partial WS is just V, partial SZ is XY, plus partial WV was just S times partial VZ. That's just a constant then, so that's your 0. Plus partial WT, 3t squared, partial TZ will be 2YZ. So you just want to simplify, and then you can substitute in for your terms if you want, but not really necessary unless asked. So 4RZ plus, that one's just VXY, 0 plus 6t squared YZ. So you could, if needed, come in here and substitute for R, where is it? V and your T with those given functions. Or just leave it. I mean, it just depends on the situation. What form is really better. So I'll just put a little note there. So we could sub if needed. We'll just put in the blue. There we go. Okay, so that's the concept. You'll have a few to practice on that. Let's look at a formula. So this is going back to implicit differentiation, and we're going to use this to find a formula. So this is kind of neat. It'll make implicit differentiation a lot easier. Although I don't really want you to memorize it. It's kind of nice to know. All right, so let's take a look at this. So find a formula for implicit partial differentiation. Okay, so for example, so first we'll do an example, then we'll do the formula, and then we'll use the formula and see how much easier it is. That's the idea. So find dy dx if y squared is equal to x squared plus sine xy, and that's it. All right, so you can see, obviously, hopefully, it's impossible to solve this thing explicitly for y. You just can't do it. Not with your y squared and your xy inside the sine. Okay, so that's the problem. All right, so we assume that y is a function of x, like the function exists even though you can't say it's explicit. So x is the independent variable So what you do when you do implicit diff is you differentiate both sides with respect to x. So we say d dx y squared equal to d dx of x squared plus sine xy. Then when you see y, you got to say y prime. So this is 2y times y prime, or d by dx, equal to 2x, and then plus the derivative of sine is cosine, so it's cosine xy, times what's inside. Now what's inside, it needs chain rule. No, it needs product rule. Derivative of the first, which is 1, times the second, plus the first times the derivative of the second, which is 1 times y prime. Like that. Okay, so now solve for y prime. So we collect the terms that have y in it. So this one and this one. So we got to distribute cosine and then collect those terms. So we end up getting this. So 2y y prime equal to 2x plus y cosine xy plus xy prime cosine xy. And so now, I guess that's what I was trying to say earlier. These you got to get together on one side because they have the y prime in it. And then we'll factor out the y prime. This was a little premature, apparently. No, not there. Could have just highlighted. Let's just highlight the x's or y primes. There we go. So we want to solve for the y prime. Now you have that isolated, or we will, and then you factor it out. So we get 2y y prime minus x y prime cosine xy equal to 2x plus y cosine xy. Factor out your y prime. 2y minus x cosine xy equal to 2x plus y cosine xy. And divide y prime, therefore, is 2x plus y cosine xy all over 2y minus x cosine xy. All right, so there's your dy dx. All right, now what we can do is derive a formula for implicit in this case. So you essentially create like a level surface, level curve. Yeah, like you have your function y equals f of x, y, and then you basically say capital F of x, y is equal to 0. And then you implicitly differentiate that or use partials on capital F. All right, I'll show you. Just check it out. So suppose x and y are related by capital F of xy equal to 0. And y is equal to f of x. So how we write that then is we say f of xy is equal to y minus f of x is equal to 0. And now we consider that. And we're going to let w equal capital F of xy, which is x of f of x. So now your independent variable is x, as we know. And we use partials on that, the first theorem. So this is one independent variable case. All right. Then take a look now at dw dx. Do we all see why it has to be just a d? Because it's just one independent variable in the end. So you say d. Anytime you see an actual d, it's one independent variable. If you see partials, more than one independent variable. So dw dx is equal to, and I'm going to change up notation for simplicity. We're looking at this now. So it's this whole partial, and then dx dt, dx dx, and then f prime. I'll show you. So it's the whole thing, partial f x of xy times dx dx is just 1 plus partial fy of xy. We're hitting the next variable times dy dx. Okay, we know dx dx is just 1. So you get partial fx of xy plus, oh, we are assuming that this is equal to 0. So this whole thing equals 0. So partial f of xy plus partial fy of xy dy dx is equal to 0. Now solve for y prime, which is your dy dx. Well, that's easy, right? I mean, just subtract your partial fx and divide by partial fy, and you got it. So dy dx is equal to negative capital partial fx of xy over capital F partial y of xy. Now go back to the previous example. I'll just rewrite it, but let's now differentiate this using this formula. So check this out. So here's our example. Find dy dx if y squared, same thing, is equal to x squared plus sine xy. So then what you do is you set capital F of xy equal to y squared. So you're setting equal to 0, right? So it's y squared minus x squared minus sine of xy equal to 0. So we're setting everything equal to 0. I wrote that wrong. It should just be xy. And you can put parentheses around that xy if you want. Now, that's your capital F set equal to 0. So now do those partials independently and see what you get. So now you say dy dx is equal to, and then calculate this, and what do you get? So try it. Oops, didn't mean to do that. Okay, so calculate this, and then compare above. Okay, so what you get minus, and then partial fx would be negative 2x, and then minus cosine xy times y over 2y minus cosine xy times x. Little simplification, and you get 2x plus y cosine xy over 2y minus x cosine xy. 2 steps, and take a look. You have exactly the same thing. This and this. Exactly the same, using this partials concept instead of implicit. So that's really nice, isn't it? So not necessarily something I want you to memorize, but just like that's what this new math will, not new math, that's what this will help you with is using partials and this new techniques, we can do things a lot quicker. Okay, that's it for 14.4. Yeah, that's it for 14.4.